you can see the presentation. Pete, can you confirm that at one more time at your end?
Yes.
Perfect. Nirmit and Jeba, I will refer to the slide title as we move along so that you can also join in there. So welcome to the ARM eInfochips course webinar to discuss the challenges of lower geometry design with optimizing ARM cores. I'm the Chief Business Development Officer at eInfochips and be hosting this event. To be joined by Peter Levin, Director of Marketing at ARM, Jeba, Senior at eInfochips, and Nirmit Patel, Senior here at eInfochips. With the presentation with ARM giving us an overview of the Design Partner Program, followed a deep dive by eInfochips on the technical topic. Feel free to type your questions in the chat box on the WebEx. At the end of this session, we will try and answer as many questions as possible. The recorded webinar will be made available within the next few days. With Peter, I would like to hand over to you.
All right. As just mentioned, my name is Pete Lewin. I work in the Partner Enablement Group at ARM. The reason of this group is to ensure that our partners can get the best ARM-based products designed as quickly as possible with the lowest risk. To achieve this, many of our partners look for a design house to partner with, either take on the entire design of their SoC or assist in particular areas, such as optimizing the power and performance of the ARM Cortex processor. Selecting a suitable design house to work with, however, is not always a straightforward task. You need to not only consider their technical expertise, but many other factors. For example, do they have the correct controls in place to handle your sensitive information in confidence? Are they financially stable? What are the standards and controls? To have the necessary resources available to meet your timescales and a large enough engineering team to mitigate any risks to that schedule. For me, a key to in choosing a design house is your experience with the IP that you'll be using, because it can help reduce your risk. You'd rather that they gained that experience whilst working on a previous project than on yours. To identify design houses with experience of using ARM IP, we created the ARM Approved Design Partner Program. eInfochips are a founding member. Members have undergone a comprehensive audit by ARM, covering all the factors I just discussed: technical experience and expertise, success of previous design projects, and good governance and financial stability. Access to ARM technical support team, and any issues to be resolved quickly directly with ARM. This ARM to confidently recommend them as great companies to trust with your complex design work and your success. We have a network of 6 partners in the program, offering a diverse selection of options across the globe, with services, capabilities, and specialisms. Those are available on our website at the address shown on the slide.
Are you there? We have Peter. Okay. I would just give a quick overview of eInfochips and then bring in Jeba and Nirmit to talk the specific technical challenges that we are going to discuss today. So eInfochips is a product engineering design firm. We have been in business for 21 years now, and we provide engineering services across the globe: USA, Europe, Japan, and India. And our design services include providing services on the silicon side with design, verification, physical design, hardware, system validation, mobile and cloud enablement, as well as embedded systems. Give you an overview specifically about our services in the ASIC and FPGA solutions. We include RTL design, simulation, FPGA design, IP integration, verification services, including development of verification IPs, physical design from RTL to GDS2, layout migration, sign-off and DFT services, as well as validation and prototyping and chip bring-up. With brief overview, I would like to hand over to Jeba to bring us to the next slide deck. So Jeba, on the agenda overview slide. Slide 8.
This is Nirmit, and Jeba will cover on 16 nanometer physical design challenges as well as Cortex implementation from ARM. Nirmit, I'll cover on low geometry physical design challenges targeted for 16 FinFET plus. Here I would like to target first will be the physical design related challenges, and then sign-off related challenges also will be discussed for a few points. So when we talk about 16 nanometer FF plus physical design flow, there are multiple challenges associated with this, with 3 steps during physical design and sign-off. Implementation, we have several challenges. That is, the one bigger most is a universal fin grid. So other technologies, we cannot put our at the chip at anywhere at the measuring grid. Here we have to also follow universal fin grid as well. There are addition of some boundary cells for left, right, top, bottom, corner, which are also not available earlier. So standard cell also has to develop these to also maintain that potential DPT rule violations on cell abutment and placement, which honors VT implant related mean area issues as well. Next challenge comes while doing extraction. Is a 3D modeling required, because this FinFET is basically a 3D, and introduction of FinFET, it's very difficult to do this 3D modeling of fins. For MUL structure, which is basically middle end of line, which was not present in earlier technologies, which is only early technologies only consist of back end of line and front end of line. Now there is also additional layers which are middle end of line, which connects base layer to M1. Do mean area, the additional margin requirement for setup checks due to DT misalignment. If physical verification, we have to have same mass spacing related rules to be also checked. The additional FinFET rule in the layer checks, and cut-out degeneration is a additional utility, and cut-out related checks are additional to previous technology nodes. Major challenge is fin boundary aware dummy OD and polyfill, as DPT aware dummy metal insertion. I'll take your round floor plan and placement restrictions now. Basically, FinFET devices has to be manufactured on some grid. It is not only manufacturing grid, but it has to be also on as well. So the new restriction comes that any standard cell or IP also has to be intermultiple of fin grid. And cell or IP or anything, when placed on the ASIC, it has to be all aligned on the universal fin grid as well. So if we just see this image, so grid is defined, but on top of that there is a fin grid. So grid also has to be followed by I mean, any of the IP, basically you have a standard cell, you can have a memory, or you can have SerDes, PLL, anything has to be released on FinFET now. metal layer restrictions. So with FF Plus technology, we have min width rule for preferred direction and non-preferred direction of metal. Example, if we take M4 as a metal layer, preferred and min width is lesser than non-preferred direction of metal for jogs. So it has also placed a big restriction on the jogging, as well as it has placed also additional restriction on IP development, because earlier to 16 nanometer technology, IP could use different direction for routing, as well as our top level can have a different direction for preferred routing. So there is a difference now. Now everything on a chip. If we take M4 again, if we choose horizontal as a preferred direction, then even IP, SerDes, PLL, or anything else has to have that M4 preferred direction as horizontal. So this is a very impact on the designers as well, and especially on layout designer. Moving to next topic, SCA impact. Here first I would like to cover temperature inversion. As we move to lower technology nodes, so the delay temperature relation becomes completely inverted. So previous technologies like higher nodes, as temperature increases, delay increases. But now at lower nodes, delay really decreases with the increase in temperature. So the ST engineer has to really find out the difference of timing corner for ST sign-off. So if we first bullet, which is setup related corner, at 16 nanometer minus 40 is the worst corner because it's the largest delay. In technologies, it was 125 degrees centigrade. Another issue will be when the PNR done and A is a different tool for sign-off check. There is big correlation issues because of a tool maturity as well. So we have the additional D-rates as well, and it takes some time to have that D-rate meets STA sign-off criteria. We'll explain double patterning timing related issue where we have to have some additional timing corners. So if we hear double patterning capacitance issues are more prominent now. So I mean, the same metal, there are two different masks, and this of the masks are getting measured separately. So there is a chance that these two masks also can misalign. So for the metal layer, the mask shift left or right creates different capacitance in the same metal layer polygon, or even move up and down and create different capacitance. So here, cross capacitance corners also getting added. Challenges solution. Next slide. So here I'll just briefly cover what is a double patterning here, and move slightly deeper into the double patterning issue during PV. So double patterning is nothing but that we are decomposing the same metal polygons into two different masks so that none of the polygons are going to be fabricated in the same mask. So if at first T-shaped space where polygons are there, there is no way we can divide these three polygons into two separate masks where two polygons are different masks. The same with U-band, jog structure, and U-band large space issues as well. So this creates a very big impact on a router, that it cannot blindly use any U-shaped route or any other route. It's to be double pan aware routing. Right? There's a related design issue. Standard cell basically are the building blocks of our PNR digital implementation. It has a two different aspects. One is a standalone standard cell generation and the full standard cell. Let us speak about only one standard cell. if we do that one standard cell, we have to take care about these double patterning issues within that standard cell itself. So if in the image there are blue and red stripes and two different masks, and it can be configured in multiple ways for a single standard cell. So the spacing plays a very, very important role in standard cell because they are pretty much small and very dense, and that M1 and M2 structure available in standard cell is very carefully created now in 16 nanometer. Moving to the whole cell library, we create multiple varieties of standard cell, and we allow PNR engineer to place them any sequence. Any cell can abut with any other cell. So it's a lot of permutation and combination, and all the combinations of standard cell also satisfy this DPT, double patterning rules. So that is also another big challenge when it comes to standard cell standalone design as well as library design. Now to the next one, we basically routing challenges at PNR digital implementation. So if only straight lines spaced at minimum distance, it is very easy to differentiate them into two different masks. There is not a big challenge, but early phase of PNR tools were very smart enough so that they dropped a lot of jogged wires on lines when connecting to higher metal layers, and that started creating related issues. More is split stitching those as well, but that easy for foundries. So basically TSMC doesn't follow that as strictly. So we have to restrict that our router itself not to drop such say jogged wires. So in our tools were that really capable enough to understand every rule of double patterning, and it has to be a lot of manual intervention that time. Two PV challenges. Next one, double patterning issues, a real life example. Here these all lines are metal 1 within the standard cell. White enclosure is basically a double patterning violation. Is happening due to that encircled via 1 which is getting dropped on metal 1 pin, but it is slightly offside, and hence creating the double patterning issue with the next metal polygon. Once the VI is moved inside that metal pin and aligned perfectly well, this violation goes off. So this small test case has been taken into consideration to explain that what even PNR tool makes a small mistake, and we come across a lot of such double patterning related issues. Moving similar test cases in the next slide. Here the white enclosure is very big and covering a lot of more polygons. So if I talk about this, what happens is there can be this such enclosure can be even hundreds of micron long. It can be even 300, 500 microns long, and covering a lot more polygons, like thousands of polygons. And during that time, it is very hard to figure out which polygon is really contributing to this. And there were cases where multiple polygons are creating such violations. So if we fix one polygon related issue, the enclosure becomes slightly smaller but doesn't disappear. So there are multiple polygons which are creating double patterning issues. It takes multiple iteration to fix it in one shot. It doesn't get fixed in one shot. So it takes a multiple iteration, and it eats out time. Especially it is when there is a time-driven tape out, not able to estimate exactly when we will be able to fix all double patterning related issues. IR and EM impact. There are multiple things, which is basically one is temperature inversion again, as well as corner selection. If our temperature issue, just a degree of temperature, like 115 degree to 125 degree, the instant drop has been hot. So we need to really be careful that which temperature our chip wants to operate, which is the worst temperature, and we have to select that way. Moving on variation, like M40 C worst corner and 125 C best corner, there is a very big difference in instance drop again. So we are really very careful when we choose the corner for IR and EM. The entire the calculation goes wrong, and we may not be able to converge silicon, even post silicon. One which is one real life block related example about static analysis. In this port is basically the highest static drop region, and we really fix them because the drop here is more, and there can be multiple reasons. There can be a very high resistive path, less number of stress here, more cell densities here. So we have fixed this by getting more robust power grid and multiple bumps on such regions. Based on flow and methodology related issues and fixes. So move to 16 nanometers, the PNR tool was not mature enough, and hence it's giving a lot of patterning related shots, but not exactly knowing that whether it is a real shot or a false one. And PNR tool used to put a lot of effort to fix those shots as well. So as a result, what happened is when 16 nanometer we started, our test case, which usually takes 1 day of runtime, it took 9 days of runtime. Still, it was not clean on double patterning issues. Leakage number comparison, and the different one where we put 2% limit for ULVT cells, 20% limit for LVT, and rest all SVT. And we see leakage power difference also as a difference, and control that leakage power as well. One is one of the real life block execution challenge with 16 nanometer very high cell density block, where if one first to go, the entire red marks are really congested region, and we have a lot of metal related issues here. This is the really very initial picture when we just allowed to do the placement and do the routing, and became really very dense. So if we see, the cell distribution is much more uniform than the previous one, and red spots get reduced. And after multiple iterations, so if we see the final one, we much clean, and the blue spots are pretty uniformly distributed across the block. So congestion has been really reduced by a great extent, and almost zero now. And there are a couple of techniques also explained here that once it was forced as a hierarchy driven placement, as well as added a lot more density blockages in that central region, so that the cell will spread apart. So now I'd like to hand over to Jeba for Cortex A platform implementation related challenges and solutions. Hello, Jeba.
Good morning, everybody. So today I'm going to talk about the A5 implementation. We have gone through the journey while implementing performance, power, and area. So really I will be covering the journey including the implementation methodology and STA journey. Moving next slide. Quick on Cortex A5. Cortex is one of the smallest application processor from ARM. So it's really targeted for the applications like low-cost handsets, smartphones, tablet computers, set boxes, enterprise networking equipment. So this project we have chosen A5 because this was our IT chip. So basically we want to target on the low power, so that's why we have chosen A5 for our implementation. So, the A5 block overview. So the size of the block is to 1.2 mm square, basically 1.152 by 1.22 mm. We have implemented it on the 14 nanometer TSMC process. We have got close to 3K gate count, and there were macros. So these 15 macro counts are hitting the primary, secondary cache memories. There are memories. And we wanted to target on 450 megahertz. Later on, actually, we have optimized this A5 with 70 megahertz. So I will be talking about those implementation challenges and the journey on the slides. And this A5, actually, we have used Cadence SoC encounter as the tool. A5 macro placement. We have placed the different macros, and so the ports are placed over the right side, right upper side. The reason is that when we looked at the top level the chip, so dependent placement of this A5 and the other blocks tune the port placement. So that's how you can see all the ports are placed on the right upper side, and the L1 cache memories are placed on the right upper side, which are very close to the ports, I ports. And these are the L2 cache memories, which are to the bottom left, and that is ITAC 0 and 1. There are the memory TLB memory, which bank 0 and 1, and D tag memories. So this has 4 memories. So basically, if you look at it, these memories we have chosen as different banks, basically, to get the to increase the performance. Basically, if you divide it by different banks, we really gain some performance, basically the speed. So we did a couple of benchmarking analysis before choosing these macros, and we have tried with the different aspect ratios, depend our different floor plan experiments, and then we have fine-tuned the memories, and these are the final ones. Implementation we have did to target, optimize our power. So what I mean is the power gating. So we use the power gating cells or the intent of A5. If you can see those highlights. So these are power gating cells we have placed in a regular interval. If you can, see the next, if I can zoom into one of the power gating, you can see that power gating cells, there are, power grids routed. So we have placed this power gating to make sure that wherever the vertical power routings are there, we just place them. So make sure that we have a, better power mesh for our. So here you can see that VDD top VSS and VDD on. So VDD top is our chip top power, VDD power. VDD on is the internal supply, which is gated through this power gating cell. If I can go to the next one, zooming down to that power gating cell, this is a dual height cell. So the most rail is the VSS and the bottom most is also VSS. The other one is VDD on, and see the VDD top over there. So this VDD top would be directly connected from the top level power stripe. So in A5 we have used metal 7 as the top layer, since it's a 14nm technology, and the metal 7 VDD is directly connected to these VDD off signals of power gating, and where the sleep enable signal is on, the power enables that, and then the VDD on would be getting generated, and VDD on would be supplied to the entire rails of A5 block. So whenever we want to power on A5, so we actually enable all the sleep enable signal of all the power gating cell. So the complete A5 block is getting power on. The implementation challenges. So, few of the challenges while implementing this A5 Cortex. The first one you can see, there were some filler cells missing, or wherever there is a small gap between two cells, the smallest filler cells were not getting inserted. When we started doing PV, we have explored that there are a lot of barrier violations, and when we debugged it further, we could find out that filler cells were not inserted. We have looked at our flow, and we could see that in the flow, the smallest fillers available in the library was enabled in our flow. So we have enabled them, and then challenge the site violation. So here, in some places we could see track libraries inserted, or instead of 9-track cells. So in this A5 chip, A5 block, we have used all 9-track libraries of TSMC. So, but some cells were picked it from 7-track library. So we started looking at it. We could see that of the 7-track library, not all cells, few of the cells, the track was not right. Basically, the cell height of 7-track library was incorrectly edited. Change 9-track cell height. So the flow, the tool is picking that 7-track library since that cell height was not correct. So erasing it. So then we have figured out, and then we have changed our flow. Basically, we have put it in the list of all the 7-track libraries, and then was picking the right set of standard cell. The other challenge is that we have a lot of timing failures, especially on the MEM2 reg path. And we looked at it, we could see that it was because of the huge access time over the macros. So we further debugged it, we could see that some of the ports, the MEM2 clock to key path of some memories, basically on the ME ports, number from the dot lib were wrong. So basically, you could see the numbers from 600 PS to 720 PS. So those parts it was failing. So then, when we did the design and started debugging it, we could find that those are the critical paths. So then we have trained them through the SDC, and we had set them as a false path. Naming sign off, slide number 28. In Cortex, we complete sign off STA with the nominal voltage of 0.9 voltage. Basically, did the sign off STA including signal integrity and OC analysis using prime time. And this is the OC numbers we have got it from our spec, and we have added them in our SDC. We have in the SDC. So here you can see that this A5 we have we had 4 setup corners with the SSG, and for hold we had 12 corners, 4 with SSG and 8 of them with FFG. So there are different OCV factors for different basically setup SSG, hold SSG and hold FFG. And look at the right side, the first one setup SS corner, we have add these switches in our SDC to take care of this OCV timing. So this you can see the hold SS corners, these are the commands we have used it, and hold FF corners, these are the commands we have used it. So for hold we have used the uncertainty as 150 as per these rating factor. Move floor plan organization. It started with the first floor plan, MS1.0. Have placed the macros in such as per the data flow. So basically, here you can see the cache over the upper side. Those two banks. Those we placed it very close to the port. The reason being is that these are the primary memories, cache memories, and these are kind of heart of the CPU. So the A5 block speed is directly linked with this the placement of the access time of this memory. So we want to keep it far from the I/O port, so we have placed them very close. And the L2 cache memories we have placed in the little down, and the rest of the memories we have placed it somewhere on the right side and the middle. And you can see over here the congestion is too high on some of those ITAG memories. So that is that all those I/O ports are actually routed over those ITAG memories and connected to the blocks which are sitting on the below or left. So fine tune the floor plan. You can see MS104. So I have changed the floor plan a little bit by considering the congestion and timing, but still congestion improved a bit, but not as expected. So then fine tune it further. MS1.5. Here we have changed the floor plan more. So he have moved those ITAG memories from close to the port to off the left side. And again the congestion is right here on the between ITAG and cache memories or the top right side, those big memories. So here again we have noticed that most of the I/O ports are routed over these L1 cache memories, and the L1 cache memories, the top metal is metal 4. We actually had 2 horizontal metals over this L1 cache memories. So that's the reason where we have seen a lot of congestion over this region. And we have fine-tuned it further on in the MS1.6 version. We have completely changed the floor plan. We have moved the L1 cache to the left side, top left side, and then we have the ITAG on close to the port. Quickly here, we have changed the I/O port placement as well. As you can see on the right side, we have actually spreaded those I/O ports. So here our objective was to remove the overlaps over the macro, and at the same time to reduce the congestion. So actually we could reduce the congestion a lot, and timing also got converged. So you can see on the graph, initially started with MS1.0 where the congestion was really, really high, and then we started fine tuning the floor plan. So the congestion got converging. Then MS1.0 the congestion was completely 0. So MS1.0 we didn't have any shorts. We could solve all the shorts, and congestion was completely 0. And we could find the timing as well. Technology, slide number 30. So we have used clock gating cells wherever possible. The reason is that we wanted to optimize the power wherever possible. So along with gating, we wanted to optimize power more further. So as you can see in this picture, there are a couple of the clock gating being inserted. Some are very close to the register, and some of them are somewhere in the middle of buffers. So for clock method, for CTS, we have used 2 different NDR rules. For leaf clocks, we have used a single width spacing. The reason is that these are the really short nets, and those are in low metals. For the trunk nets, we have used a double width and double spacing. Basically, these are really, these are running really huge. As I have mentioned, the size, is around 1.2 MB. So some of the nets were running almost close to, 600 to 700 micron length. So we wanted to use a two with two spacing to reduce the resistivity on the nets, at the same time, to avoid any signal integrity or blinking, basically. So using Cortex A5, so Cortex A5 has one inbuilt facility that it has a single clock domain. So this single clock domain helps to symbolize the process of clock insertion at the implementation. And its clock domain crossing, if you have a clock domain crossing, it would be really challenging to is the clock tree. Last one, it makes it simpler to support a clock grid if required. For example, if we want to have our own custom clock tree, we can do that. So ARM Cortex A5 had that feature to customize it for the customer need. Move slide number 31, clock optimization. Original clock tree structure. You can see the clock U we could gain around 280 PS. And we have on the right side you can see the final CTS optimized clock tree, where the skew is optimized to close to 200 PS. So if the first one and the last one, the skew we could optimize close to 70 PS. And if you look at that buffer count on the initial and the optimized one, we could almost reduce around 400 buffers. So optimize basically this is directly linked with the leakage power and the total power. So basically we could optimize the power a lot. Moving next slide, 32, significant IR drop benefits. So here is one of the the experiment we have did it. So we actually tried with the traditional CTS and the CC op. So in CTS we have seen that most flops were switching in the window of 100 PS, and we have seen a lot of IR and EM violations, EM issues. So then tried a couple of other experiments with CC opt. So where CC opt is kind of it's a concurrent clock optimization. It's basically it optimizes the clock, and then it tries to optimize the data path as well. So it currently tries to optimize both the paths, and it gives us the best clock tree. So you can see that the yellow line highlighted. So here most of the flops were triggered in the window of 250 PS. So here the advantage is that, as you can see, the dynamic power, so compared to the left side window, so the dynamic power reduced a lot, because at the same time not all registers are getting triggered. So if you look at in every time instance, the number of registers triggered is reduced. on DC optimization. So actually so we haven't seen any timing degradation, but in time we could actually improve on IR drop and EM. Timing slides. Next one, timing results. So okay. So I have mentioned earlier. So initially we started with a 450 megahertz of speed, and then we wanted to optimize it to 470 megahertz. So when we try with 470, we have seen some of the timing violations on the path. And we have tried different experiments, and we have tried different techniques to solve them, but some of the paths were still failing. So then we decided to try LVT swap. So after LVT swapping, we could achieve the setup of in pre-CTS close to 70 PS, and post-route setup is degraded to close to 328 PS. And the short hold was 2.3 NS. So we have tried a couple of iterations, and we have tried the ECO optimizing both setup and hold. So here we could bring down that setup to close to 180 PS, and the hold we could brought it down to 328 PS. So we have did couple of iterations of ECOs, and so then finally we could actually both the setup and hold with 470 megahertz. So in the journey of this timing STA fixes, we have tried different experiments with the different techniques, and the best results we have got it. So yeah, we could close it with 470 megahertz. More slide. We actually in this the journey of AFI Cortex implementation with with trying with different techniques and scripts. We increase the speed by percentage, and the area. So basically, we have tried different aspect ratios, different floor plans, different experiments with reduced and reduced area of this A5. And on the final optimization, we could reduce the area by 90% of what we have targeted initially. So the power we could optimize it by 8%. So this is including the CC opt technique we have used, and some of the custom CTS optimization we have used, and some of the paths we have actually fine-tuned it with the with the different techniques. So the power we could optimize it by say 8%. So numbers are compared to our initial target, we could actually optimize it by these numbers. Couple of challenges, especially let's say when we if you want to optimize more technology like 16 nanometer or 10 nanometer, so we should be really careful because of the DPT rules. So because of this DPT, as we've seen in other projects, so then the routing is getting derouted a lot because to solve the DPT related DRCs. So we need to be really careful. I mean, we have to really work close with the ATA in mind, because just to fix the DRC, the tool may be routing really long and with adding a lot of buffer. So that may impact our STAs. So we really looking at it very closely to optimize it. Especially if you want to optimize the core like A5 or A57 or any of the other ARM Cortex, we need to be careful and we need to work very closely. In terms of optimizing the A5, the core or any other ARM cores, actually we try with the different techniques. As we have tried in this chip, we have actually tried with the different techniques to improve PPA. So I mean, it all depends on how we tweak the settings and how we optimize the things. so we can actually optimize it as per our target. So with that, I am just opening for the Q&A session to ask the questions.
Thanks, and thanks, Nirmit, for covering this segment of the presentation. So I have a few questions that are popping up on that box. So the first question, Jeba, for you is, what was the utilization of this A5 chip?
Okay. So initially we have tried it with 57, close to 57% of utilization. We have tried with different aspect ratio and floor plan. So one of the main objective for us was to optimize the area. So we progress further, and as we fine tune further. So in the final optimized one, we could achieve it by the utilization of 70% with manual inversion to close the critical paths, and so we had more so we had to do a lot of iterations of ECOs as well to close the timing because of this the compact design. So answering the question, so our final utilization was 70%.
Thank you. One more question coming in here from Manan. Were you able to optimize the power grid and improvise routing resources for the IR drop? And what are the techniques to improvise your power grid?
It's a pretty critical challenge when we actually focusing on power optimization on any of the ARM core. It is a power hungry processor. So I'll give you slightly background, Manan, here that we had 8 metal layer stack here to use for a power grid for this block, and we had different experiments to figure out which is the exact power grid suitable for this one, which basically sort of taken care especially about this routing congestion related issue, routing resources as well as the power requirement. So with different experiments, we started earlier with multi-layer power grids. Almost we had all layer power in initial experiments when we just started at lower utilization, which is basically 50-55%. And we had all layer power grid M1, M2, M3, and all the way till M8. But as we moved on further, we needed to reduce the power metal stack, and we had to skip some of the metal. And we had come across some of IR drops, so it was a lot of back and forth, and finally we arrived at skip layer power grid. And we had skipped, we had grid in M1 and M2, then skipped the 3, 4, and then 5, 7. It was basically a very good route sources as well, and would compact our cell. So it's all about our power grid optimization here, and along with every power grid change, we had to check that IR drop, state dynamic as well, and power EM, to ensure that our power grid is basically correct. On top of this, there are a lot of experiment on which VIA type to be used on the power grid. So last we arrived at 4 VIA or rectangular type. So basically that VIA and 4 array for same VIA layer for each cross section on the metal IR layer.
Okay. And what final power consumption, both dynamic and leakage?
Sir, didn't get the question.
Final power consumption, dynamic as well as leakage.
to answer your question, say, okay. So we had power grid and ULVT not enabled. We have various power leakage power, but when we had to open enable low VT and ULVT cell as well, so finally we had around 120 milliwatt as a dynamic power and 80 milliwatt as a static power issues.
Okay. What the question that's coming up is, what was the improvement in the block size in terms of die size that was achieved?
Right. Okay. Thanks for that question. That's one of the good questions. So initially we have tried with the aspect ratio of 1, and then we started with the area of 1.57 mm square. As per the logics and the other routing related things consideration. So then we've tried a lot of the floor plans, and we have tried with the different aspect ratios, and finally we could reach to the 1.4 mm square. So basically 1.225 by 1.25. So if you look at it with the with our initial floor plan and the final the one which we have finalized it, so overall area we could gain is close to 9%. So if you look at that die size in our IoT chip, so basically we could optimize the area close to 9%. Yeah.
Thanks, Jeba. Thanks, Narmit, on answering questions. So we have a few more questions coming up, but in interest of time, what we'll do is we'll respond back to them offline. And I wanted to thank everyone for joining this webinar. If this has been a useful webinar, please do write to us at arm@marketing.com, at eInfochips.com, and we'll make sure that we'll keep you posted on the upcoming webinars as well. This webinar will be available for download in a few days, and so we will be sending it out to all the participants who have joined today's webinar for reference as well as for future use. Again, thanks Pete for joining us on this webinar. Much appreciate your time, and thanks Jeba and Namit for leading us through this. Thank you everyone. Have a good day. Bye now.
Thank you everybody.
Thank you.